Guys, welcome back. Hope you've got that idea of resultant. Have we got any Facebook prompts on that?
No one has written back. Perhaps the break was too short.
Okay, okay.
I'll tap you on the shoulder once somebody...
Okay,
yeah,
that's fine. Guys, as we're going to this next part, I know this is where a lot of you get lost. So if you're not following, Facebook us, phone us, 086 1058 262, and I'd love to speak to you.
Yeah.
So if you're having a problem with work energy, inclined planes, we're going to be doing this question. There are so many questions that have come in about this. But if you get this one right, then I'm sure you'll be able to answer tomorrow's one. Remember, it doesn't matter that you can do 3 years in a row, but you need and look at the model answer and make sure you've got those, learn them off by heart. That's not going to help you. You need to make sure that you can do them from first principles.
Yeah, so the basic principles.
Understand what to do. Okay.
Okay, so, and also just tell me on the page. I will tap John and I will interrupt him if there is something on the question that you're not understanding.
Okay, cool. Great. Now, we're not going to spend all day on work energy, so get your work energy sorted out right now. Okay, now remember what we were doing. We were talking about the idea of resultant, and I hope you've got this. So let's go back to my component diagram, and this was this diagram. And what I need to show you is that if we look at the component diagram, it shows us what the forces are. We recognize that those two forces, the normal force and the force perpendicular, they're equal. So they're going to cancel each other out because they're equal in magnitude, opposite in direction, which means that the only two forces that are really acting on this body are these two forces, the force of friction and the component of gravity, of the force of the earth, parallel to the slope. So what do we mean by resultant? Now, this is something that you do need to know, and it's almost unfortunate that maybe you haven't spent enough time on it, but forces are vectors, so we can draw them as arrows, and when we want to get the resultant, we draw the arrows head to tail. So there's the tail, there's the head, and when we add them together, we can do them like that, then we'll say that this added these two together, that will give you your resultant. So that's the combination of those two. So it's like saying, let's take the frictional force, because they're in the same direction, and the force that is the component parallel, and we're going to add them together to give us our net force. I sometimes put it as FR, which is resultant, but you could easily say that's F net. Okay, so please understand what resultant is. Resultant is the overall effect. If we've got the frictional force down and the force applied, if it was being pulled up the slope, for example, then we would find that the force applied minus the frictional force would give you a resultant. But if you add them in this case, they're both in the same direction. You're just going to have to recognize they're both down the slope.
Well, John, I've actually got a question here from Rahila on Facebook. Hey, lady. She's giving me some nice compliments on the other side. She was wondering, is the parallel component not in the opposite direction to the frictional force?
Okay, that's a really good question. So let's just make sure that we understand why it's not. In this case, I want you to see what's happening. And it's really important that we've got this right. If you look at this diagram, which shows you the section, remember what I said to you, gravity always pulls down. So if we look at this diagram here, we recognize that that would be the component that is perpendicular. Okay? Now, remember that's perpendicular, and remember that we would say that this is the component that is parallel. Now notice, it's this one plus that one gives you that one. So it's that one plus that one gives you that one. The reason I know that that's the case is because the object is slowing down. There's nothing pushing this object up the slope. Remember, when we read the question, it says the block was moving at constant velocity. It then hit the bottom of the slope, and then all the thing that is acting on it while it's moving up is to pull it down. Gravity is trying not to get it high. Gravity doesn't like things to be up in the air. That's why when you throw a ball up, what does gravity do? It pulls it down. In exactly the same way, in this example, the box is sliding up the slope, but what's pulling it down? It's the gravitational force as well as the frictional force. So Rahima, I hope that helps you understand why there isn't a force of pushing it up. Gravity doesn't push, gravity pulls. Okay.
What does it do, John?
It pulls down. Okay.
Everyone's going to remember you in the exam tomorrow.
Okay.
Yes!
Yes, we've got it. Okay.
Well, and I think Alan Fizzy on Facebook, he says, is it possible that a question may arise asking us to show only the components of a free body diagram?
Okay. Now, guys, remember, I've shown you both examples. They usually accept both. It's unlikely that they will ask you specifically only draw the components. But they could. There's nothing stopping them. But what I'm suggesting to you, make sure you understand the components.
Yeah.
Because if you understand the components, then you will see that there are these two forces that are acting on the box. There's the force of friction as well as the force that is parallel to the slope.
Cool,
okay?
Cool.
Okay, guys, so if we're going to now work out the work done, because that's really what we're now going to take all of this working to try and answer our question. So let's just go through the important part of the question. What we were asked to do is to calculate the distance x that the block moves up the slope. And so what I'm going to do is I'm going to choose a clean page. I just want you guys to remember this diagram here, and we're going to remember what we've done on forces as well. I'm going to go to a clean page and let's see what we can do. We're going to say work energy theorem tells us F net is equal to the change in kinetic energy. We've worked that already. And we found that the value for F net is equal to minus 2160 joules. But we also know that F net is equal to, W net, not F net, is equal to F net, which is the resultant force. That's why I was dealing with free body diagrams just now, because we're going to need to calculate the F net, times delta x, which is the distance, which is the thing we want to find, times the thing that everyone battles with, and they throw their hands up, cos theta. Okay? So what I want to do is just break it down into little bits. We've broken down, we've got the W net. We know what W net is. We have explained what F net is. We know F net is friction, the frictional force, as well as the component parallel to the slope. Okay? And now we can see we've got to explain the cos theta. So I want to just explain cos theta for a minute. That cos theta, remember the definition of work, requires us to say the following, that if the force delta x and f, if they're in the same direction, this object is accelerating to the right, okay? Then what we would say the angle theta between these two vectors is going to be 0 degrees. If you want to, put them head to tail, like I showed just now. So put them head to tail, that's the head of the one, that's the tail of the other, and you can see that the angle between there is they're in the same direction. They're not pointing in opposite direction. They're in the same direction. Theta is 0. They're parallel to each other. Okay. Now, what I need you to understand is what happens if we've got the opposite situation. So if an object is moving like we've got here, delta x, and we've got a force of friction. Now, what's the angle from the head of that one to the tail of that one? I hope you can see that's in the opposite direction. So theta here, we're going to say is 180 degrees. Okay. And all it's just helping us to recognize is if they're in the same direction, the cos of theta over here, when it's 0, cos of 0 degrees is going to be 1. But cos of 180 is going to be minus 1. And that's because they're in opposite directions. So here, we've got this one in the positive direction, that one in the negative. They're opposite direction. That's why we need the -1. Okay, so let's now apply that idea. Hope we've sorted that out. I think there were some Facebook questions on cos theta. When is it positive? When is it negative? When is it 0? When is it 180?
Yeah.
I hope I've answered that.
I hope so too, guys. If there is anything that you don't understand about cos or anything, please just quickly pop me a mail right now so we can just address it as quick as possible. Yeah.
Okay, right. Hope we've got that sorted out. And now we're going to go on to the next part of it, and that's to... Oh, we got a question.
I don't know. I just saw Malaji, and all I saw is, please tell John that before he closes that topic, he must... What? He must leave us with the appropriate formulas for that chapter, such as formula for friction work done.
Okay, we'll do that.
Okay.
Malaji, we'll get to that.
Yeah.
Okay, cool.
You see how he got me there?
Yeah, I did. Right. So we're solving that original question, and we're just going to write it out again. F net, sorry, why did I say F? It's W.
W net.
Indy, aren't you watching?
Oh, no, because I said F, well, W net, F net.
Yeah, let's make sure W is for work, F is for force. Guys, I know it's a hot afternoon probably where you are, but let's concentrate. Let's make sure we don't make mistakes. W is work measured in joules. Force, F, measured in Newton. So let's not get too carried away. So remember what we said. This F net is going to be the combination of these two. It's going to be the frictional force plus the component of the gravitational force parallel. So I'm going to just put that into this equation. And I'm going to say, yeah, I can do that, can work out what that is. I'm going to separate them out like this. Say it's the frictional force plus G parallel times delta X times cos theta. Now, some of you might say, well, we could have done it another way. Yes, you could have. You could have said W net is the force of friction, and I think that's what Malaji's asking. I think that's what he's got. We'll come back to that arrangement of formulae. But here, this will make it really easy. But what we first of all need to do is to try and work out what this thing is. What is this FG perpendicular parallel? So, yeah.
Well, I've actually got a question from Marshall. He says he's actually about to give up because he's completely lost, and it actually has to do with that. He says he doesn't understand where the FG parallel is from.
Okay.
Yeah.
Let's just go back to our diagram. Good one. Thanks, Marshall.
Don't give up.
Don't give up. Please don't give up. Okay? Yeah. Remember what we said. Let's just pretend for a minute that this slope didn't have a frictional force. Okay? And an object moving up a frictionless slope that was very, very, very long. Okay? So we pushed something up the slope. Do you think it would just carry on going up the slope forever?
No.
No. Well, look, we know it won't. Yeah. Why? Because here's an example. The slope is a little bit steep, but if I do that, what happens? It had an initial velocity, but what happened? It came down.
Yeah.
So what was pulling it down? Well, you know it. Of course you know it. You've done vertical projectile motion, so you know that there is a force that pulls things down. So even if it was on a slope, there's still the part of gravity, the force of gravity that's pulling it down the slope. Okay, so I hope you can see that, Marshall. I hope it's helped you. And that's why we say we've got this bit as well as that bit. So we've got the frictional force as well as the force parallel. And what we now need to be able to do is to calculate the size of this. So how do we do it? FG parallel, this one, okay, is equal to, we're going to say that that's an angle. That's the angle theta. That angle theta is the angle of inclination. So what we're going to do is we're just going to apply a little bit of trigonometry. And what we're going to say is that's opposite. This is opposite the 90 degrees, so that's the hypotenuse. And so I'm sure you can see that we're going to use sine theta. And so we're going to say it's FG, the hypotenuse, times sine theta. Okay, so FG parallel is FG times sine theta. Malaji, I hope you're watching, because FG is what you were asking about. This was one of those formula you must know. FG parallel is FG sine theta. If we then need to break FG apart, remember what FG, it's the mass times the acceleration due to gravity times sine theta. Okay, so there's a formula to remember. It's not on the data sheet, and you need to know how to work it out. Just by the way, because I don't know where they might do it, but they might do it with something like static friction. They could ask you for FG perpendicular, and FG perpendicular would be this equation, Fmg times cos theta. So those are two really important equations to know. So we're going to substitute into this one and work out Fg parallel. So what was the mass? The mass was 30. We know that G is 9,8. And in this question, we're wanting sine of 15 degrees. Okay, so when we put that into the calculator, we get 76,09 newtons. And I'm just going to quickly put that value into my equation here. And I'm going to say I knew that the force here was 450. I know that this is plus 76,09. And I'm now going to substitute my values in for work. Minus 2160, which I worked out earlier, times delta x times cos theta. Now, remember, in this particular example, what are we doing? The block is sliding up, it's going up, but the forces are pulling down. What's the angle theta? 180. And so we're going to put that 180 in over here, and that will give us the minus 1. When you work all of this out, what I found was that this gives me minus 2160, and this value here comes to minus 526,09, and times delta x. So now the arithmetic is there. Delta x is equal to 4,11 meters. And we've answered it. Guys, I hope you can see. If you do it step by step, break it down, it's not as difficult as it seems when you first look at it. Okay.
Okay. Should we go to a break?
We'll go to a break now?
Yes, and we'll be back after the break.
After the break. See you then.
See you then.